So expressions become very easy to work with, right? And it's certainly based on very simple theory of how shape information can be extracted, how the local geometry can be extracted. The other side of thing is, well, you have global shading models, and you say, well, surface radiosity is really a property of the radiance that is coming off of other surfaces as well as from the source. Okay. So this is where now you have to account for everything else in the scene as well. Right? So these are global shading models. The advantage of this is, of course, your accuracy goes up because I'm accounting for not only some distant light source but all the neighboring sources. But as you can see, the disadvantage is the model is far more complex, and inferring all the parameters in the model can be quite problematic. It becomes sort of a rather ill-conditioned problem to solve. So how do we overcome some of these problems? Right? So what are the issues that we have seen with these models so far? We've kind of seen, if you will, increasing complexity models, right? And from simple things to more complex observations. And of course, the more complex they are, the more realistic they become because they're explaining truly all the interactions that are happening when you capture an image of an object. Trying to relate the observable intensities to the scene. But we realize that as we make it more complex, you have many more things to solve for. Your unknowns are growing at a rather exponential rate. And you have to start making assumptions. And in general, you're optimizing many parameters that are codependent. They're not independent parameters. Right? Optimizing for independent parameters is nice and easy. But if you think of the fully complex global shading model, so under that, what are we doing? We are saying that there is some distant light source. I don't know where it is, but I'll model it as being distant. So my expression in terms of the radiosity due to that is relatively simple, right? It's the albedo of the object times normal dot product of the source. Great. So that I can do. So that's a component of my model. Then you're saying that, well, there's additional components to it because of neighboring objects. So the neighboring object is a distant light, a nearby light source, and of course it's an area light source. Right? So we express its radiosity value in terms of what we saw. So now in that I have to compute the orientation of the other object with respect to the object of interest. In order to do that, you will have to know the geometry of the other object with respect to the geometry of the current object of interest. Of course, those geometries are unknown, so you have to make some assumptions. So I'll make some assumptions to start with. I don't know the amount of energy coming off of the close by light source. Neither do I know the amount of energy from the far away light source. Right? All of those are initial assumptions I made. So all of those parameters are to solve in some iterative fashion, some optimization condition. You can imagine that this becomes a rather recursive problem. I have to know the radiosity of all neighboring objects with respect to the object of interest. Then I say, okay, if I solve that, what's the difference between what I've observed and what I just computed? Right? Somehow the difference then has to be propagated back to all my sources and has to be propagated back to define the geometry of my neighboring objects. Then I repeat my entire thing, compute the intensities and the geometry of the object of interest, still probably see some errors, then recurse everything back. So the question is, when do I stop? I may keep having to do that for a very, very long time. It will become an empty problem. So it's very difficult to solve these things, right, without appropriate constraints. So if I purely look at it from a vision standpoint and say, given an image, if I want to recover the geometry of an object, what would you conclude? Can I ever do it? Almost impossible. Almost impossible for me to do. So, well, what do we do? Do this before we really know. The point of knowing all these things when we conclude that we can't apply it. Well, we can apply, right? We simply have to figure out how to constrain our solution. So what do we do? Well, what if we knew some of the things that we just talked about as unknowns? So, well, that's exactly what we do. We start creating scenarios where we convert some of the unknowns into knowns. So, well, one of those approaches is called photometric stereo. Okay. So what do we do? Photometric stereo. We say, first and foremost, let's start again simplifying things. We'll say that the object is Lambertian. Okay. So great, we can start simplifying things. We'll assume we're going to use a local shading model. So not worry about all these complex objects interacting with each other. We just say it's a local shading model. And we also come up with a set of known light source directions. So I have to solve for an unknown light source direction. Let's just say we know it. Right? Wonderful. Now I can take multiple set of pictures of that object while varying the sources of direction in some controlled manner. So I end up with a set of pictures where I'm assuming what my surface is like. I know my source and I know the direction of that source. Actually, more specifically, know the source direction. We don't know the amount of light because under a local model, you remember, we don't really care so much. We lump it into some constant factor. As long as I know the direction of light, I'm happy. And then, of course, we will also assume that let's not worry about all these distortions between lenses and everything. Let's just say orthographic. Right? So our images are nothing but orthographic projections of what we sense. And based on this, we say, well, go back, let's say, reconstruct the shape of the object and compute the albedo of the object. All right, so we've done a nice job at constraining our problem, right? So our problem becomes camera. We know S1, S2, Sn. We have no geometry on how we are capturing the image of the object, and say, well, go back and reconstruct the object. So this becomes now essentially the problem where I want to estimate the surface map given multiple images where the light source is known and the imaging geometry is known. Okay? So it becomes essentially a problem of figuring out how some varying surface gets projected onto my image. All right, and how do we do that? So, well, in general, if you had some surface in an XYZ plane, its corresponding projection onto an XY plane, well, we can explain it based on normals, right? Local normals on that surface. So if I have some local normal, let's say, right, some orientation of the surface, local patch, I have a normal to it, I have a plane, it's getting projected, right, so along the z direction. Because remember, we are assuming orthographic projection, right? So any surface we have is simply getting projected onto the orthographic plane, so intersecting plane is z equal to 1. So, well, great. So I have some light source, I have normal, so I know the source, I know the normal. Well, I don't know the normal. But how do I compute the normal? Computing the normal is relatively simple. Any given point in the surface